guys, I'm Trent. Most of you probably know me. It's really a pleasure to be here as usual, and today I actually have two talks. First this one, and then the other one. But the other one actually, I'm gonna just keep that a bit of a surprise unless Daniel already said what it was. But okay, so I'm gonna give this talk, and then we'll have a bit of a break, and then I will give the other talk. And I think you want to stick around for the other one too. I think it'll be fun. I'm gonna try something I haven't tried before, and no, I'm not getting naked. So this one though actually is a drill down on ocean, and I'm going to zoom in on a couple of the angles, the aspects of ocean, for those of you that might be interested. And with it though, I will actually start with an overview to give you guys a feel of what's up there. And the other talk, well, like I said, it's a surprise, so you have to wait. So this one, the title is Curated Proof Markets and Token-Curated Identities in Ocean Protocol. What does that mean? Well, let's start at the beginning, and let's talk about data and incentives. My very first summer job ever was working for the Canadian government, where I was given a data set of 20,000 data points. Back in 1997, this was still the AI winter. And I was told to basically accurately classify among 13 different classes of audio radar signals. Everything from like tanks driving around, to birds flapping their wings and flying around, to people walking and so on. And at the beginning of the summer, within a week, I had a very basic, stupid thing working that could get 55% accuracy. What that meant was it was wrong 45% of the time. But I had a whole summer to work on this, and I worked hard and I worked hard, and I couldn't believe that people were paying me to do AI, so I worked like 14-hour days. I loved it. In the end of the summer, after iterating and playing around with neural networks and genetic algorithms and a bunch of other AI, I managed to get the accuracy to 65%. So 10% improvement for a whole summer. And so 65% still means 35% error. 1 in 3 times it would fail. Are you going to rely on that? Not at all. It's basically useless, right? And this was actually the state of AI back in the late 90s and early 2000s, where you would have a summer student or a full PhD to basically sink their teeth into a data set and to try to get better results and outcompete algorithms and so on. And in the end of the day, most of the results were so bad that you could not deploy them, right? And that was what I did. I actually did it for a second summer too and managed to improve another 7%. So, and if you think about it, it's actually super embarrassing, but there it is. But what happened in the 2000s was there was a paper in 2001. Microsoft researchers Banco and Brill, they published a paper that said, okay, normally people are competing right here where they've got, say, 100,000 data points or 20,000 like I had, and they're going to compete with their various algorithms, whether you've got a k-nearest neighbor or some perceptron or something else. And you're going to be happy to be 5% different than the next guy, right? The thing is, they all kind of are terrible, right? But what they did was they said, you know what? Let's not change the algorithms. Let's just add more data, right? So they went not just 2x more data, but 10x, 10x more, 10x more, 10x more. What happened? Well, the accuracy went way up. It went from 75, 80% all the way to 95, 99%, right? And this was without any new PhDs. This was just adding more data, right? 1,000x, 10,000x more data. And that is actually like, yeah, a huge embarrassment to the AI community, right? All this time that I spent to try to get, you know, better radar data and so on, or better radar accuracy, I should have just went to my superiors and said, hey, you know, I need more data, right? And I didn't. And so this actually kind of, it turns out, changed everything. In the mid-2000s, Google published a paper called The Unreasonable Effectiveness of Data, hence this. And what they realized was, we want more accurate models to sell you more ads, of course. We want more accurate models. How do we do it? We don't hire lots and lots and lots of PhDs just to get more accurate models. We just buy a lot more data. And so they bought Google Maps and satellite companies and all this. And ever since then, they've been basically aggressively gathering data. And it's not just Google, it's Facebook, et cetera, and the rest, right? And so they call themselves AI companies. That's a head fake. It's really, they are data companies. So, and by May of 2017, there was an article in The Economist where data is considered the world's most valuable resource. So you can see there's this direct lineage from the 90s where AI researchers were just playing around with these fixed data sets to the 2000s where the companies like Google and Facebook realized that data was the truly valuable thing, to the mid-2010s where the rest of the world is starting to feel the pain, right? And we see the pain every week with things like the Facebook issues last week, and of course that was just the latest in a long line of Facebook issues. And what they all realize is if they have more data, and of course they don't want to share it, they want to silo it, then they can build better models with more accuracy, make more money selling ads, right? So they have this default incentive, a shelling point, to hoard the data, to silo the data. That's the problem, right? And it can come down to, you know, this, you can predict this in a sense if you understand the incentives. And Charlie Munger, who has worked closely with Warren Buffett for decades, says, show me the incentive and I will show you the outcome. And frankly, if there's one thing you remember from both my talks today, remember this. Show me the incentive, I will show you the outcome. It always comes down to incentives, right? And so we go back to the data silos. They're incentivized to sell more ads. Therefore, they're incentivized to have data silos, right? Data silos, not good, but more money, good for Google and Facebook, et cetera, right? So they can't help it. It was just the incentives. But there's an interesting thing with incentives. We now have this new thing that I like to call incentive machines. They're more popularly known as blockchains or public utility networks. But at the core of them, they have this amazing feature. Of course, they're decentralized and they're immutable and all that. But the most amazing feature is you can get people to do stuff. How? You pay them in magic internet money, aka tokens, right? So if you add value to my network, if you do stuff that I want you to do, then I'm going to give you tokens, right? And that is really the superpower of blockchains. They are incentive machines. You can use blockchains to shape incentives. So, going back to the data issue, well, we had that shelling point of siloing the data. Let's change it. Let's change the shelling point to pooling the data, right? How? Of course, blockchain technology, right? And that's basically what Ocean is about, is changing the shelling point about data from data silos to pooling data on behalf of freedom and democracy and all that, of course. But then the question is, how do we do this, right? Like, that's the general high-level thing, but what does it look like, right? And so as we were starting to design this, going back even a year now, we found ourselves struggling. We didn't have a structured way to think about it, and as far as I know, no one had at the time. But over time, we kind of struggled and struggled for months, and then we kind of had a revelation, and that the revelation was, what if we could, well, there was two revelations. The first one was, token design looks a lot like optimization design, where you're designing these optimizers to maximize objectives and so on. And what's cool, I had done that for a long, long time as part of my world of AI for 20 years. So that was cool. And then I realized that if token design is like optimization design, then let's approach token design like optimization design, right? And what are the steps in optimization design? Well, it's formulate the problem. Then it is try to apply an existing solver. And then finally, only if needed, you invent your new solver, your new optimizer. It turns out that for tokens, we can do a similar thing. But instead of solver, we replace that with pattern, or crypto-economic primitive, if you like, right? So that's really a methodology that we realized that we could do, which is these three steps, right? Formulate the problem in terms of objectives, constraints, and design space. And this comes down to asking, who are the stakeholders? What is the give and the get of each? What do they want? What do they want to do? What are the constraints? What are the possible attack vectors? And then what is the design space? What can I move and remove and so on? And then in terms of patterns, there's a whole bunch of possible patterns, right? With respect to curation, with respect to governance and so on, and to try them. And hopefully one of those will work, right? For example, token-curated registries are something like 1/3 of all new blockchains because they solve a lot of the problems nicely. And then design that new pattern. And in fact, a list of patterns here is, this is just a subset, but we've got curation patterns, and there's a bunch of new ones emerging just in the last year, right? We've got, I mentioned TCRs, Token-Curated Registries, which is basically a list of stuff, or more precisely, a set of stuff. A whitelist, a blacklist, whatever. Then we can actually stack those so that we can basically move from one list to another list to another list to get promoted, whatever, and that's what's called a stake machine. My colleague Dimi came up with that. It's pretty cool. It's sort of like a riff on state machines, but with staking, right? We've got curation markets, which is for continuous valued membership. And then curated proofs markets, and I'll be talking more about that because we found that we needed to come up with a new pattern, a new building block, in order to build Ocean. And then in terms of, so that's one pattern, right? Curation. There's a whole bunch of things in curation. But there are other patterns too. There's patterns with proofs, and this is really the very, very heart of the system. At the heart of any system, as you saw in the last talk, you really need proofs. Proof that some sort of work was done, right? Such as solving a puzzle, in a cryptographic puzzle with Bitcoin. Or Filecoin, it has a proof of space-time. Did you store this file for X amount of time? Yes or no? And you can even have human proof of work, like Steemit has, that you actually entered some information and it sticks around, right? Augur has a similar idea. And also data availability and more. And there's other sort of proofs too, other patterns, identity patterns. There's a whole variety there, reputation systems, governance, third-party arbitration, the list goes on and on, right? So these are basically the emerging building blocks in this space, right? Just like, in the world of software engineering in the late 90s, there was a book that came out called Design Patterns by the Gang of Four, and that became sort of a key textbook in the emerging realm of software engineering. And there was a few other textbooks around that time too, or books that became textbooks. We don't have these textbooks right now for token design, but the ideas are there, they're forming, and in the next 1 year, 2 years, 3 years, 4 years, we will start to see these textbooks emerging. So in this talk, I talked about the high-level goals of Ocean, and then I've talked about this sort of approach to designing tokens. But what I want to do now is drill into some of the patterns that we actually used to give you guys a feel of what these look like, and then what is a walkthrough of how usage in Ocean might look. So I'm going to talk about 3 main things. Curated proofs markets, which is basically a market for proofs that actually has curation. I'm going to talk a little bit about token-curated registries for identity. And finally, I'm going to talk a little bit about data availability and other proofs. So overall, I've had other talks that really explore sort of all those steps in great detail, but in this talk I really wanted to drill into some things. So after a lot of iterations of looking at who the stakeholders were and asking many questions like what do we want to optimize for, we arrived at this idea of we want to maximize the supply of relevant data. If we can do that, data is really a supply-side problem. It's a gas that expands to fill available space. So there's always demand, right? There's always going to be AIs that want to eat the data, So if you can actually get the supply and make it really easy to access, then you're in good shape. So we want the network to basically be supplying as much data as possible. And it can be price data or free data. So this was really the objective function, the thing to maximize. And so then, though, with that objective of Ocean, we convert this to block rewards, okay? And block rewards as in, Bitcoin gives 12.5 Bitcoins every 10 minutes if you solve that puzzle, right? Well, we looked at the question of let's reward by making relevant data available when asked. So if I'm asked to give data that I have, that it's relevant, then I make it available. But then the question is, what does it mean to be relevant, right? How do you know that it's relevant? And maybe some people have some definitions, some people have others. What do you do? And the answer is, it's actually really hard to get a computer to decide that, right? There's lots of work in information theory, for example, or in the world of big data to come up with relevance measures, but they're all only essentially half measures because it really comes down to what the community cares about, right? But then in that word community is the answer. And community means the community can decide what's relevant by voting with money. That is staking, right? So how do we know what's relevant? Algorithms capture this poorly, so we leave it to the crowd, the community. We let them put their money where their mouth is, and that is staking. So basically, if I think that a data set is really important, I can stake more on it. I can use Ocean tokens to put more stake on it. And curation markets are interesting in that if I stake earlier on a given data set, then I actually get more stake than if I stake later on the same amount, right? So it rewards early adopters. And that's actually a key thing because you want to be incentivized to act faster rather than sooner. What this maps to is, for this overall objective function, to maximize the supply of relevant data, then the revised reward, block reward, is reward curating data, that is staking on it, and making it available when asked, right? And so that's basically what this objective function drills down into. And we'll go one step farther here. And it comes down to this pattern. So you can write the block rewards as a function, right? And in this case, what it is the expected rewards of a given actor for supplying a particular data set is proportional to how much they have staked on it That is, what they have predicted about its popularity times its actual popularity. How many times did they actually serve it up, right? And then the tokens during the interval. So in Bitcoin, for example, it's 12.5 Bitcoins every 10 minutes, right? So this is a simple formulation that shows what the block rewards manifest as. And this basically then comes back to the objective of maximizing the supply of relevant data. So therefore, every time someone serves up a piece of data, right here, then they can expect that they're going to get a reward proportional to how much they have staked on it. And it's actually not quite proportional. It's actually a log of that. And that actually avoids the stake whales and promotes diversity of many data sets. So, but this is kind of the core of what's going on. So overall, what we call this is a curated proofs market. So it's a market for proofs, a marketplace for proofs, where people are proving that they made data available. But then those proofs are actually curated, right? So a proof of making dataset X available might have different value to the market than a proof for making dataset Y, because maybe dataset X has 10x more stake on it, right? Now we ran into an issue with this, and the issue was, well, there's a few. One of them was privacy, right? So there's a lot of cases where the data cannot leave the premises or shouldn't leave the premises. Things like German medical health data, right? It can't leave German soil, and it makes a lot of sense too practically. So you want to be able to potentially pull the compute to being on-premise. What's traditionally done, of course, there is they only compute on-premise, and they don't figure out a way to reconcile data sets in a lot of other places. That's actually solvable now with things like federated learning and AI. But the overall challenge is privacy for on-premise compute. Or actually decentralized compute too, with things like multi-party compute. So there's a few ways to approach privacy-preserving compute. Another challenge is some data is really heavy, right? If you've got a data set that's 1 petabyte big, do you really want to send that over the wire to someone else? Probably not, right? So you want to have it stay on-premise, even behind a firewall. And finally, there's actually a whole bunch of emerging decentralized compute for AI or privacy-preserving, right? Everything from SingularityNet to Enigma, right? And so there's a lot of emerging services. Wouldn't it be great to take advantage of that rather than Ocean trying to swallow that as well, right? And so what we realized was we could take this overall block rewards function and generalize it ever so slightly. So instead of being just a predicted popularity of making data available or a proof of making data available, it's actually of a service. That service can be making data available, but it can also be doing some form of compute. And it even generalizes beyond. So we generalize just a little bit in the block rewards function. And what that means is that Ocean is rewarding curating of services and proving that it was delivered. And once again, this is a cryptographic proof, right? So that's basically what Ocean is at the very core then. It's maximizing the supply of relevant services. So overall then, there's actually two pieces to this, right? In this thing, there's the expected popularity and the actual popularity. And what I'm going to drill down into each of these now, I'm going to drill into each of these now. So I'll start with the curation market, and then I'll also talk about the proofs. Actually, looks like I'm talking about the proofs first. So, all right. So let's get to that. So yeah, proof of data availability. There's a whole bunch of ways to do this, actually, right? And there's emerging ways all the time. So the question is, if I make a data set available to you, how do you know that I'm not lying to you, right? And so a very, very simple, straightforward way is saying, well, let's use the cryptographic proof that Filecoin has been working on, right? Which is proof of space-time. And proof of space-time is a mechanism to prove that I have stored some data for a particular time in a particular place, right? It's actually overkill. It's more than you need, but it actually solves the problem, right? Because Filecoin says, Filecoin doesn't want you to store data on S3 and then take it last minute and make it available, right? They don't want you to do that, and they have a way to manage that. Ocean doesn't care. So, but if Filecoin has solved overall, then that because it's a superset, it's a workable way. Another way is we could have a challenge response mechanism, where in the idea of TrueBit and others, where I make a data set available to you, and if you're happy, you're happy, and if you're not, then some third-party referees are randomly chosen from the network, and then they basically provide arbitration services. And at the end of the day, I either lose stake or the challenger loses stake. And there's other approaches too. Jason Toish from TrueBit wrote a paper on Christmas Day. He published it about data availability. So that was my Christmas present from Jason. So thanks, Jason. So the point is, there's a bunch of proofs for things like data availability, which is the core of Ocean. And in fact, it goes more generally, right? So in terms of compute style proofs as opposed to human proof of work, we've got proofs related to data and computation. So I've talked about proof of space-time. I've talked about proof of data availability. There's at least two more: replication, the fact that you're storing data more than one location; proof of service receipt. And then in terms of computation, there's an emerging variety of proofs too, everything from zero-knowledge proofs and their variants like ZK-SNARKs, ZK-STARKs, and so on. Interactive proofs, things like full homomorphic encryption, where you can literally compute on an encrypted data set, which is, feels like science fiction, but it's actually possible, and even possible efficiently now for certain classes of problems. And then also we've got secure enclaves like Intel SGX and so on. And the cool thing is, with supporting more proofs, going back to, going back with more proofs, then what that means for the user is more services available through Ocean, right? So, for example, we've talked about the data availability, right? We can have it for just data blobs, where we've got things like Filecoin plugging in, SIA, Swarm, storage, but then also structured data, right? And this is where things like good old BigChain, I can't help but mention BigChainDB, or OrbitDB. By the way, this isn't the Orbit logo. This is Samuli's Twitter logo, because I couldn't find an Orbit logo. I guess he doesn't have one yet. And Fluence and other emerging decentralized databases, right? And the cool thing is, a lot of these are very complementary. And that's really for data availability too, but it's now structured, right? And then there's general compute, things like iExec and Golem, or prediction, which actually can be framed like similarly, Augur, Gnosis, these folks. And then there's tweakings of compute for various things like SingularityNet and Synapse AI for AI framed compute, or privacy-preserving compute like Enigma and some of the new Cypher tools. Also linking in interoperability among networks via the likes of Cosmos, Polkadot, Interledger. And finally, this last one is actually pretty interesting. There's some protocols emerging that are basically wrappers for proofs themselves. And TrueBit is a really nice example of that. So if hooking into TrueBit, under TrueBit, it can actually give you proofs of various things in quite a clean way, leveraging challenge response and so on. And Oracleize has actually generalized towards this too. They initially started out being a data oracle, then a decentralized data oracle, but now they're actually covering compute proofs too. So that's quite nice. So Ocean is designed to be basically a layer that incentivizes the connection of all of these, right? So it's a curated proofs layer, and each of these services are incentivized to be hooked into Ocean simply because of the block rewards. So that's kind of the core of the proofs thing. Now let's talk about the token-curated registry. So with Ocean, there are some attack vectors, right? So I should first of all ask, how many of you have kids, daughters, age, anywhere up to age 10? Anyone here? We've got quite a few actually tonight. Cool, cool. So you might appreciate the Elsa and Anna attack. So, so any of you who has young daughters has been subjected to the movie Frozen again and again and again. Let it go, and so on. And actually, it's a great song and it's a great movie, but in doses of less than 100 per year. So, and basically, actually, this is, if you Google search for Elsa and Anna attack, then there's actually literally pictures of Elsa. This is Elsa, I know this, attacking many people. Anna actually never attacks. But in the context of blockchain, what this means is, imagine someone takes the movie Disney Frozen and they put it onto the Ocean network, right? And then they start serving it up and they start getting block rewards for that. But of course, they don't have the copyright to that. What do you do, right? And there's other attacks too. There's the data escapes attack, where people take data out of the system, right? And you don't want that because they'll just share on their own. Or maybe you do want that in certain cases. Or curation clones. So if you're not early in curating, why not take that same data set and create your own curation market within Ocean, and then try to get all your friends on that one, right? Or Sybil downloads. So basically, what if I just go and stake on something and then I downloaded a bunch myself to earn all those block rewards? But maybe Ocean says, well, you can't do that because you're yourself. But what if there's a ring of us all colluding, right? So how do you handle that? So this is an example of a few attacks. The white paper talks about this, and there's some details for each, of course, and more attacks. We actually have a list of pages of attacks. Now one way you might say, okay, well, if you act badly, well, we're just gonna, catch you and send you to jail via court of law, right? and or basically, you know, get the law after you somehow, right? Like you broke copyright, see you in court, right? And actually, that's an interesting way of thinking. And in fact, this is kind of how we kind of approached it when we did Ascribe, you know, several years ago. But we realized, we've learned that it's not a good idea for these blockchains to be tied to any given jurisdiction, right? If you are tied to a jurisdiction that is tied to a courtroom and so on, then that's a massive attack vector, right? If that jurisdiction decides that they don't like what's going on, they can stop it and they can cut you out, right? Like we've seen where Turkey, for example, has turned off their parts of their internet, and other countries, right? So you do not want to be dependent on one jurisdiction for anything, right? At that base layer, it's super important to be permissionless and borderless, right? But at the same time, you do want to handle these attack vectors, and at the same time, you do want to have recourse, ultimate recourse towards legals and so on. And we've come up with a heuristic that I like to call sunny day tech, rainy day law. And what that means is 99% of the time, you have incentives structured well enough such that on that raw-based network, that is permissionless, borderless, people are incentivized to act well, right? And it converts the idea of a zero-sum game to a positive-sum game if you do it well. And you'll see what I mean shortly. And then one level up, you can actually have people pinning identities and legal third-party arbitration, et cetera, to Ocean, but and they can tie to their own one jurisdiction, but there's a bunch of these pinning to it, right? So there's no single entity at that higher level. And by doing this, then we actually get the 99% case, or hopefully even higher percent, yet at the same time, there is recourse with legals, et cetera. Sunny day tech, rainy day law. So how do we do this in Ocean for the sunny day tech? We do it with a token-curated registry, a TCR. And TCRs were developed heavily by the ad chain folks about a year ago for internet ad exchanges. And basically what it is it's maintaining a set of stuff that's curated by the community. In our case, it's a whitelist, a set of the good actors. Anyone who is basically good enough to participate in the network that the rest of the community has agreed, yes, they're okay. They're not spammers, they're not malicious. There's no reputation beyond that. It's just basically they are not bad actors. And so how does that work? Well, you have to stake to get in. So here we've got new user B. Bob wants to join the network. So they stake, say, 10 tokens, and they say, hey guys, I want to join. And there's a period in which anyone can challenge them, 7 days, 28 days, whatever. And during that time, in this case, we've got existing user A, in this case Alice, says, I'm going to challenge you, right? And so then basically at the end of the voting period, there can be one or many challengers. And then if there has been at least one challenge, then all of the community votes that wants to vote, and the 51%, if more than 50% say yes, B gets to go in, well, they keep their stake and they get the stake from the challenger. Or if they lose, then the challenger gets the stake. And that's the core. So basically, people are incentivized to vote such that the overall value of the tokens goes up. You're incentivized to have good actors and keep with the bad, right? And this is basically the mechanism by which you can do it. And so it's a proxy for identity, but it's very, very simple, lightweight identity. It's only about is this basically public key a good actor or not? No more, no less, right? It has no other concept of identity beyond that. It's just enough to basically nudge things from a zero-sum game to a positive-sum game. But there's one challenge here, and that is high-friction onboarding, right? You've got a waiting period of 7 days or 28 days. But what if you want to get going now, right? And you know, it's like, you know, 10 people in the network, and they're saying they're having a wonderful time, and they're making all these Ocean tokens from serving up data and curating and all this, right? You want to be a part of it, and you want to get data sets. So what do you do then, right? And so we have a second way to get into this, a second way to onboard, and that is with risk staking. So you basically vouch for others. So in this case, let's say that Alice knows Bob. And so Alice says, hey, I'm going to put down 10 tokens on behalf of Bob. And Bob can now join and start participating immediately. And Bob can actually grab my tokens and run with them. Just run away and take them. But because I trust Bob, I know that Bob won't. And maybe I misjudged, and then Bob will take my tokens and I lose my money. But in general, I am letting Bob in sort of this web of trust fashion, and I'm putting my money where my mouth is in terms of trusting, right? And in that way, Bob can start to participate immediately. Now, I don't have a slide for this, but there's also a third mechanism as part of TCRs, and that is, at any point in time, if someone thinks that you're acting badly as a bad actor, then they can challenge you to kick you out. And if the community votes to kick you out, you're out, and you lose your stake, right? So, so for example, in this case, let's say that Alice vouched for Bob, but Bob, Bob came in and started acting badly. Well, then Bob will get kicked out. And very possibly Alice will too, because she's clearly a poor judge of character, right? So Alice is actually thinking long and hard about whether or not, of who she might let in, right? But as time goes on, then this incentivizes this growing community of people that actually know each other and work with each other and trust each other with actual dollars. So now what's cool, going back to this, these attack vectors, the summary is this whitelist of good addresses these, right? So the whitelist of good actors addresses these. And there's very particular explanations for each that I don't have the time, but if you want, the white paper talks more about that, right? But in general, if someone's acting badly by uploading, Elsa and Dana too much, everyone kicks them out. They're like, hey, this is going to actually hurt the overall value of the network. You're gone, right? And they lose their stake, and they also lose their block rewards. So what I'm going to do now is talk about Ocean from the perspective of a walkthrough. And in this case, Ocean is designed where you can have higher level interfaces with marketplaces or with data commons and so on. But I'm just going to focus as if it's really the core level, okay? And I actually drew this with pencil and paper a few months ago now, actually. And I actually had converted it to computer, like with some paint programs and stuff. But I wasn't quite satisfied with those. So I'm just going to show you my hand drawings here. And I'm not quite at XKCD level, but I'm getting there. So basically, first of all, I've got about 6 or 7 slides here. We're going to start with claiming a data set. So here, Alice, this is Alice. She's got a pretty cool hairdo. She's claiming this data set X. And so she claims that she has copyright on data set X. And she's staking 50 Ocean tokens to do so. So she's putting this claim into the Ocean network, right? So now she's making this claim. And then there's actually a gating function there. So basically, others are checking. And they say, oh yeah, data's okay. So and then the overall vetting period concludes, 5 days, whatever, right? So in this case, a few people check. No one bets against her, saying, no, this is silly. You don't have copyright. So then it's in. And now, because she's actually staked some tokens already, putting stake in, it's actually a way of kicking off a curation market. It's a curation market for dataset X. So every single dataset has its own curation market. And so here, she's actually getting back, well, there's a price. So this is actually a very, very key curve. It's called the bonding curve. And what it is it relates the price to produce drops of X. So drops is a measure of stake in a given data set. So drops of X is how much stake you have in X. It's a derivative token of Ocean tokens. And so this is the price, the cost, and then here is the supply. So basically at the very, very beginning, there are 0 drops. But as the number of drops get issued, then the price to buy those drops goes up, 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 right? So this is rewarding early adopters. It's cheap here, it gets more expensive here. And it's really expensive over here, right? And so initially, the price is, it's 1 Ocean token to buy 10 drops of X. And so she's already staked that. She's actually staked 10 tokens, so that means she can buy 500 drops, right? So she's actually got 500 drops, and she actually has such high confidence in this data set that she says, you know what, I'm going to put more tokens in. So she actually buys another 500 drops, and it costs her 75 Ocean. So remember, initially it was a bit cheaper for her, but it's getting more expensive because it's going up this bonding curve, right? The price for staking is going up, right? And so she now has a bunch of stake in X in the form of drops. And we're going to see that these drops have 2 values. One of them is you can earn block rewards, like I've talked about a bit before. And also, she can actually unstake at a profit if she's good at basically understanding the dynamics of interest. So, but first of all, she's published this data set saying, I've got this data set, I will make it available. Along comes Bob. And Bob says, hey, I'm really interested in this data set, right? And of course, Alice has already promised to make it available. So he says, I'm interested. She makes it available. Bob downloads it for free. This is actually an interesting thing with Ocean. It's actually free to download. It doesn't go through the Ocean network. It actually goes directly from Alice to Bob. Ocean network is basically managing the access control. In fact, actually the authorization is a better word. Bob is getting the data set from Alice. And Alice is then going to get block rewards because she staked on X and she served when requested. So basically, Ocean is saying, hey, you're getting mining rewards for this work of making data available when asked, right? How much? Well, it's proportional to how much stake you have in that data set. And so in the end of the day, she's going to earn Ocean tokens. Just like people earn Bitcoin for mining by solving this cryptographic puzzle. That's a type of work. Same thing here. The work is making the data set available when asked. And the reward is proportional to how much you staked. The log of that, to be precise. So Bob, now we're going to talk a bit about curation. So a bit more about. So Bob, he tries the data set. He builds an AM model. Looks like we've got a nonlinear perceptron with one hidden layer here. And he tries it, and it actually manages to get down to 1% error. So he's very happy, right? It's not like 40% error like my experiences, but he's pretty happy with that data set. And he's like, great, this is a really useful data set. So he says, you know what? I'm going to stake on this too. So because he's now got knowledge about that data set, so he takes that and he puts, he basically spends 125 Ocean tokens to buy 500 drops of X. And looking at the bonding curve here, that means it's going up from a supply of 1,000 drops up to 1,500 drops, I believe. Let's see. Yes. So overall, he's spending more than Alice was spending, but it's still pretty cheap because he's only the second adopter, right? So now he's got some drops in X. He's got stake in the dataset X, right? And because he staked it, he wants to earn block rewards for making it available. So he does make it available for download. Now along comes Joe, and this is Joe. He's got a fun haircut too. So he decides to request dataset X. And now remember there's two providers for dataset X, right? You've got Alice and Bob. It randomly picks between Alice and Bob. And in this case, Bob is randomly chosen. So then Joe downloads X from Bob. And so Bob gets the block rewards because he staked on X and served it when requested, right? And his reward is proportional to his stake in it. And then there's a difficulty factor too. But overall, notice how Alice and Bob would get the same reward on average because they both have 1,000 drops in X, right? But it's kind of interesting because Bob had to spend a lot more money for those drops, right? Because he was a later adopter than Alice. So it really rewards early adopters. Now coming along, Joe, he tries out the data set, he builds a model, whatever, and he's like, wow, this is a great data set, so I'm going to stake on it too. So he buys some more. And it costs him even more money to buy 1,000 tokens. It's costing him, well, even more Ocean, right? 500 Ocean. There we go. So now we've got 3 people in the system, but another 100 come along and they download the data set because it's becoming popular. It's a really good data set, right? And so we've got Alice and Bob and Joe. They're all making the data available, and because they all have approximately the same tokens, then each of them gets randomly selected 1/3 of the time, right? And so they're getting equal rewards, block rewards. So that's the key thing here, right? So this is sort of hitting sort of steady state where there's a few people serving this up, right? Now Alice is thinking about selling stake. So this is the scenario of in the curation markets about selling stake. So she's like, should I sell stake? She's thinking about selling 500 drops of X, of stake of X. So right now there's a supply of 3,000 drops, right? And so if she went and sold 500, go from 3,000 down to 2,500, you look at the bonding curve, the average price is, the average of 5 plus 6, so it's 5.5 drops, 5.5 Ocean tokens for every 10 drops, right? So if she sells, then she gets 275 Ocean. Wow, that's pretty cool because she only initially invested 125 Ocean, right? So, and she's already got that back, so she definitely sells, right? And then plus, she actually retains half her stake, right? So this is actually pointing to the power of being an early adopter and knowing that this was a really great data set. Now let's come to Joe. Joe was also thinking about selling his stake, right? And remember, he was a bit after Alice. So should he sell? And he's thinking about selling 1,000 drops, stake in X. The average price for that is going from 2,500 down to 1,500, which means it's 3 plus 5 over 2. So it's 4 Ocean for every 10 drops. So that means he would get 400 Ocean. But remember, he actually spent 500 Ocean to put that in, right? So he'd actually lose money if he did that. So he doesn't sell. Instead, he decides to wait because he thinks, you know what, I bet there's going to be others who are going to stake and invest. And in the meantime, I can keep serving this up and earning block rewards, right? Because remember, that's the other way to take advantage. So this is basically a walkthrough of how Ocean works with sort of the core mechanics of the proofed curation market, right? You see how basically you've got people where they're initially putting their data set in and staking on it. And by staking, they earn drops of X or Y or whatever. And then with that, they can use that to make it available to others. And then by doing that, they're earning tokens every time they actually make the data available. And of course, they can unstake, potentially at a profit or a loss, depending on how smart they are, or lucky. So basically, that's the summary of the token mechanics of Ocean. It's basically quite simple. And as you see, it's an interesting mix of proof of work, where there's actual work being done, data being made available, and stake, right? So it's kind of an interesting hybrid. To conclude, so I started off this talk with talking about AI and how it has led to data silos, and we basically ended up with this data crisis, right? So we realized that we could change the incentives towards pooling data, and with that, though, it came down to really needing a thoughtful token design, leveraging particular building blocks, right? And so we came up with some building blocks. The key one is the curated proofs markets, right? And this is binding together the curation market with the proofs. And then the token-curated registry, this is an off-the-shelf building block that we did riff on in order to improve onboarding. And that is the summary of this talk. So I will stop there and take questions. Thank you.
Is there any sense in distributing the delivery across the multiple holders of the data so that there's parallelization of the distribution?
There could be, and actually, interestingly, Ocean doesn't have that built into incentives, but it will emerge. The market will find a way to, if that's an issue, it will find a way, right? Just like with Bitcoin, right? Well, the core theory of this is you can start with something that has very simple rules, and you can have a lot of complexity emerge. So with this very simple rule for Bitcoin of, you get block rewards if you solve this computational puzzle. And from that, we had all these things emerging, right? Like mining pools to average out, the variance of expected block rewards. We had ASICs, people spending hundreds of millions of dollars to build modern ASICs, and then have ASIC farms, and we have crypto wallets and exchanges and all of these things from that very, very simple core block rewards function, right? That's what we're trying to do with Ocean here too. So we're being extremely restrained on purpose, where it's just that one very core incentive and letting everything else emerge on top, and in some cases helping to kickstart things on top. We're building a reference data marketplace with DEX, for example, right? But so for this case of splitting apart the data, that actually can follow to the incentives. People would just naturally do it, right? Yes?
I think you just started to answer my question a bit there, but so just to understand, is Ocean the protocol for exchange or the platform for exchange? Actually, I should put that question any other way. Or is it the protocol for exchange and other people build the places for exchange?
Ocean is a protocol with a mainnet manifestation, although of course other people can take that same protocol and the implementations and run their own nets if they like. In the same sense as Ethereum, right? So Ethereum is a protocol where it's implemented with various clients in various languages and the yellow paper, right? And then there's a mainnet, but there also happens to be Ethereum Classic, et cetera, that's running the same protocol essentially, right? So that's really what Ocean is in that way. In terms of the exchanges and stuff, that's all one level up. So Ocean, the network, doesn't have anything to say on that, right? People can actually, there's exchanges where they have priced data, and Ocean itself does the clearing for the priced stuff. But it doesn't do any of the order matching or anything like that, right? So, and Ocean itself isn't doing any work in terms of storage or compute. It's basically helping to connect the suppliers of compute or storage and playing basically an authorization management role, key management sort of thing. So it's sort of like, or call it capabilities, right? Where you've got the authorization and the service. So you can call it a curated capabilities network if you want, right? But it's very explicitly not doing storage. It's very explicitly not doing compute. I've realized we're trying to do one thing really, really well in the Unix philosophy, right?
So incentives are pretty straightforward in this system, but people are different. And the question is, what if an incentive would become a perverse incentive, and it would incentivize people to steal data and share it, stake it quickly, and actually sell it out once they made enough. How do you go against that? Is it 1%? Because it's not with jurisdiction, so the question mark is, how do you prove that it is stolen data?
Yeah, so that's a wonderful question. And so if the data is stolen data, ultimately, this is something that would actually happen off-band in the network, right? But if you find that it's stolen and someone is acting badly, then they're going to get kicked out of the network pretty quickly, right? So this comes down to the token-curated registry of actors, where it's converting what would normally be zero-sum in like Bitcoin to positive sum, right? So it's kind of amazing, actually, how many attack vectors get largely mitigated by this. It's not full, it's sort of soft, right? It's economic incentives. But we've seen even with Bitcoin, right? Bitcoin is another approach to solving this classical problem of the cap theorem, right? Where you're trying to do, you have a network where you're trying to have all the nodes agreeing on the same thing, and you have to be partition tolerant, or making the data available, or consistent, trying to prevent double spends. And you can only have two of those three, right? Pick any two of those three: availability, consistency, or partition tolerance, right? And another way to frame that is, in the event of a partition, are you going to make the data available, or are you going to be consistent, right? And so think about Bitcoin for a second. Bitcoin actually chooses to go for availability over consistency, which is kind of strange because you're trying to prevent double spends. You know, someone might have $100 million in Bitcoins, yet the network itself has actually optimized for availability, not consistency. Yet somehow people trust to store that $100 million worth of Bitcoin. Why is that? Economic incentives, right? So Bitcoin actually uses economics as part of the key puzzle piece to solve this puzzle of the cap theorem, right? And so in general, this is sort of something that the world of security is starting to realize, is that economic incentives can actually help to help security. And we're actually leveraging it here very strongly in the TCR framing, right?
People can be incentivized to get copyright protected material and be removed or something.
Yeah, similar thing, right? So that's the also
sharing now, having people download like music or something.
Exactly, but this is where, once again, it's the also NAN attack, right? So with a TCR, this registry of actors, you have to make sure that that initial community has the values that you care about. So it's not the file sharing values. It's not the file stealing values. It's actually paying the creators to get compensated, right? Like, I have many artist friends. I like to see them get their families fed, right? So basically, then they end up being the curators for anyone else who joins the system, right? And so if there's people that come in and start taking uncopyrighted content, like copyright protected content that they don't have the copyright to, that they don't have the rights for, that's actually bad, because it means that some artist isn't feeding his family, right?
Yeah. But therefore, there must be the knowledge that it is copyright protected. So how should the people know that it's copyright protected if it's new material, for instance?
Yeah. So this is where it's all offline, right? So Ocean itself doesn't see it, but it has the link to the offline via the actors of the TCR, right? So it's incentivizing towards good behavior, because if you're found to behave badly, it kicks you out, right? So if I want to know whether something is copyrighted in this sort of challenge response, like I talked about, then I look at that file, and then I search online, and I see, you know, who is the actual copyright holder. And I'm incentivized to do so, because if you post that and you're staking on that, and I find that you're not the copyright holder, guess what? I get your stake, right? So I'm incentivized to go and find if you're acting badly, right? So that's level 1 protection. Level 2 is I can kick you out, or I can challenge to actually kick you out completely based on just bad behavior, right? So once again, it's sort of economics for security. It's interesting. Ocean has a greater challenge than Bitcoin and stuff, because Bitcoin is a very simple core proof. It's a pure cryptographic proof. Ocean is actually trying to resolve two things. It's got proofs related to maintaining the consistency of the system and stuff that it can leverage the traditional, like Bitcoin. But it also has to have sort of proof of copyright, right? The problem is that's messier, right? It has to talk to the real world more. But this is where we're leveraging staking very heavily. Different what for copyright? Yeah, well, actually, I agree that it's yeah, I fully agree actually, right? So copyright is you know, it's morphed a lot over the years. You know, initial copyright protection was only 10 years. Now it's, you know, 75 years plus life, or life plus 100 years even, which is basically overall the age of copyright is the age of Disney. That's why I referenced Elsa and Hannah too. And we dealt this a lot with this with Ascribe, and I see that what's interesting, because of networks like Ocean, where it's sort of curated on the rights, and ultimately it's not about maintaining copyright, it's actually just about compensating creators so that if you create cool content, you can pay your family, right? And because Ocean is actually solving that more directly rather than needing the government middleman of like copyright registries and stuff, then the need for the copyright laws will start to go away. And we're already seeing examples of this. Rare Pepe was the first, and more recently CryptoKitties. You know, where's the copyright on that? It doesn't exist. It's just you own it if you have the private key. You don't have copyright, but it's enough.
Right. But also created the industry of lots of intermediaries.
Yeah.
So it doesn't really pay off for the one, for the copyright holder.
Yeah. Well, it can.
I mean, the copyright holder can only hold the copyright, but the other rights.
Well, copyright laws are useful. Like if there weren't copyright laws right now, like no musician you know would be able to make a living, even the best of the best, right? So they're actually helpful in some ways, but the system right now is very broken in many ways, right? And you know, we had this experience, you know, starting on Ascribe in 2013 with basically, you know, copyright power on the blockchain, and we kind of did it a bit more old school that way, trying to bind to the old world and stuff. Here we're doing it much more softly with Ocean because we see that ultimately we don't want to be tied to jurisdiction, and ultimately we shouldn't have to have reliance on the copyright laws at all, right? But at the same time, we need to reconcile the fact that there's many massive data sets out there that are held by copyright holders, and there's actually tremendous value if we can actually get those data sets into Ocean in the nearer term, right? Things like self-driving cars, right? Get those into Ocean, and then we can actually get self-driving cars 10 years sooner, right? I'm wondering if we should pause for a break now, yeah? So maybe we'll take a 5 or 10 minute break? 10 minutes? Okay, 10-minute break and then the surprise talk, and you'll like it, so please stick around. Thank you.